So set up your work. You can talk to each other at tables. This is a question that has a couple different tactics that you can run through and do depending on how much background information you read up on. But it's going to cover a really important concept for the quiz. So start putting it together. If you got questions, you can raise your hand. So if we look at the modified question, we've got some stuff kind of started, or that I started kind of right away. What is the pH? So if you're going to look for pH, that's the negative log of the H3O plus concentration, okay, of a buffer. We haven't talked about what a buffer is. We'll come back to that in a second. That contains 1.0 molar acetic acid and 1.0 molar acetate, okay, and we're given the pKa. So what we're saying is our initial conditions are set. They're telling us the acetic acid concentration to begin and the acetate concentration to begin. Right, remember, H3O plus, or our pH, has to happen at equilibrium. So what we're saying is we've started this. Where did the equilibrium go? Okay, so we would have to figure out our change. In this particular case, how is it going to change? So let's try again. If we look at a Ka, the Ka is CH3COO minus, our products, over our reactants. One of our products is 0, which means the Ka is 0. What size does K have to be? What size does K have to be? All Ks, bar none, have to be true to this statement. They're all larger than 0. We can't have a negative K, we can't have a 0K. Okay, which means if we go through and plugged in our initial conditions, we would be at 0, which means our Q, okay, going back to our last unit, is too small. Okay, it has to get larger. To get larger, what has to happen? It has to shift to the right. Our products must increase. So we could go through and say we're going to increase, and they increase by decreasing our reactants. Okay? How much do they increase or decrease by? That's some unknown amount. Okay? So we can define what we want that to be. Right, so I could go through and say the acetic acid is going to decrease by X. Right? Regardless of what we're actually going to write here in a second, I would argue that's not a useful substitution. Where do I want to define my X? What's the goal of the question? The whole problem is to solve what? pH. And to get to pH, I need to know H3O plus. So if I'm going to try and solve for anything, I want to be explicit and swift and fast as possible to solve for the H3O plus. So I'm going to define my H3O plus as going up by X. Okay. If the H3O plus goes up by X, how much does the acetate, the CH3COO minus, have to go up by? It will also have to go up by X. Why? Not true. I can individually increase one product versus another one. There's something that controls my ability to do so, though.
The coefficients from the balance.
It's the coefficient from the balanced chemical equation. When we're saying the H3O plus goes up by X, we're effectively saying its molarity, its moles per liter, goes up by X. So what we want to do is convert that moles per liter into acetate. We do that through a balanced chemical equation. We're changing one substance to another substance. We've decided to drop those calculations because they were simple calculations. Okay? And if you don't find them simple, guess what you need to do? And since you aren't answering that question, I'm going to guess you don't find it simple. Which means every time we go through and do these, you also have to include this bit of information. Oops, come on now. Which should be mildly upsetting because that means you have to show more work for your calculations. Yay, quiz on Wednesday. How do I convert the moles of H3O plus into the moles of acetate? Where's that conversion factor found? That's the coefficients from the balanced chemical equation, 1 and 1, which is why we haven't been specifying it, because that was a calculation that we assumed that you were capable of doing. Okay? And if you're at all remotely nervous about that, that's fine. Show that work. So that when we now go through and run that calculation, we see that the acetate goes up by positive X. What happens to the acetic acid? We'd run the same calculation. Moles of H3O plus per liter. How do I convert that into acetic acid? Well, the moles of H3O plus have to cancel. The moles of acetic acid need to appear in my calculation. Since it's all 1-to-1, it goes down by X. What's my equilibrium concentration of my acetate? 1.0 minus X. Concentration of my, that was my acetic acid. The concentration of my acetate, 1.0 plus X. And then my H3O plus is X. What do I now get to do? I'll reiterate, the quiz is Wednesday. (1.0 plus X times X, 1.0 minus X. This equals the Ka. What was I given? Somewhat irritatingly, the pKa. So what would I have to do? The Ka will equal 10 to the negative 4.75. Can sub that back in down here, negative 4.75. And what can I now solve for? X. Okay. If we go through and look at that, that will be a quadratic, okay, which would mess things up and make things really ugly to calculate, but it is a quadratic and we could go through and solve that. Okay. We could make assumptions, see if those assumptions hold true within our individual calculation. Okay. But ultimately we should go through and determine what X is. Kind of, sort of? Hesitate to ask, but let's fire it out. Did anybody actually solve for what X was? Okay, that makes it a little bit more challenging to manipulate these things, okay, but we can still work through it. This is one way to set up this question. Okay, there is another. Okay, are we ready to delete everything? Yeah? What we're going to go back and do is take a look at that K expression a little bit more carefully. My Ka equaled my acetate, CH3COO minus, times my H3O plus, over my CH3COOH. Yeah? What did I want to solve for? pH. To get to pH, that's the negative log of the H3O plus concentration. Do you see H3O plus in our expression already? So what could we go through and do? It's going to get real ugly real fast. Let's take the negative log of both sides of the expression. Okay. Does anybody know some log simplifications?
If it's over and under, subtract it.
Okay. So if it's under, we can subtract. So we can say the negative log of CH3COO minus H3O plus keep that all bracketed, minus the negative log, the CH3COOH. Is that what you're saying? Oh, and I just erased half of it. Okay, so it is something we could go through and do. Do you know any other simplifications? You know the division one, what about the addition one? Or sorry, not the addition one, the multiplication one. Because the division one ultimately in this case isn't going to be all that useful. Yeah, there it is. So what I'm going to do is a subtle kind of rearrangement of this expression. CH3COOH, bracket, bracket. Can I do that? All I'm doing is pulling out the numerator out of that calculation. Why is that powerful? It's the addition. The negative log of the CH3COO minus over CH3COOH plus the negative log of the H3O plus. You know what, I've got a plus and a minus there. Should I condense those? I mean, I could. But we're actually not going to. Why should we not do that? If we brought it over to the other side, we could do that. What were we solving for? pH. What is pH? Negative log of the H3O plus. What do I have written out there? What is that? The negative log of the H3O plus, which means? That's pH. What's the negative log of the Ka? Let's look at the left-hand side of the equation.
4.75.
Your number is correct, but let's take a step back from the number. It's the pKa. So now let's take a hot second and look at this equation that we've got written out. What are you solving for? pH. Do you know the pKa? Do you know the concentration of CH3OO minus? Yes. Do you know the concentration of CH3COOH? Yes. What could you go through and do? Just plug those values in and solve. You don't have to go through and do an ICE table if we understand how to do this secondary manipulation. Do you like doing all this algebra? Some people are like, oh yeah, I definitely like this algebra. Some people just hopefully are like, no, I don't want this algebra. Is there a simpler way? Yes, there's a simpler way. Somebody else already went through and did this calculation for you to point out the relationship between those individual pieces. And by so doing, because they've created now this magical, mystical formula that gives us an answer, what do we get to do with it? Name the relationship after them. Right? And then we can just use this relationship from here to the end of time. Okay? And that means we don't need to know the algebra. We don't need to do an ICE table. All we have to do is be able to plug in those values. That's kind of neat, isn't it? Right? This expression is known as the Henderson-Hasselbalch expression. Okay? Officially, not looking like that, because Henderson-Hasselbalch rearranged it, made it look a little bit prettier. Right? And I haven't rearranged it to make it look a little bit prettier because there's some important addition and subtraction steps within it that I have not memorized. And since I have not memorized what those addition subtractions are, I have to go through and solve the Henderson-Hasselbalch every single time. What's your shortcut? What's that? The slides are great right now. They're going to be a bit of a problem come Wednesday. Okay, you've got a cheat sheet. You could define the Henderson-Hasselbalch on that cheat sheet to help you go through and solve. It's now just a question of subbing in those values. I would not be surprised at all, and sorry I don't have it off the top of my head, if this as an equation showed up on the front of the quiz. Because there's always an equation list at the front of the quiz, right? So I would actually bet Henderson-Hasselbalch's on there. Okay? Can this be made slightly more difficult? Yes, it always can be. If we look at the original question, did you get the original question? No, what were you given? You were given something that if we take that 1 molar solution of acetic acid and that 1 molar solution of acetate, they're nice in this happy little mixture, and we add 0.1 molarity HCl to that, what happens to the buffer? Okay, what happens to the system? So right away, what do you think should happen to the pH?
Go down.
Why should it go down?
You're adding more acid.
You're adding acid to this, so it should go down. The question becomes, how much does it go down? And we would have to quantify that. What is special about HCl, in particular, in comparison to acetic acid? It's a strong acid, which means HCl is going to completely convert across into H+. What is that H+ going to seek out and react with? What do positives like to find? Negatives. All right, so we could go through and look at our buffer system and say, where do we have something that would react with a positive? Well, there's no negative written in that one, but there is a negative written there. What's going to happen? The HCl will now add hydrogen to that species, which means what happens to the concentration of the acetate?
Go down.
It's going to go down. How much should it go down by? .1, because HCl is a strong acid. It's going to fully react and push that across the other side. Note that when we look at the chemical expression shown here, we're not showing this as an equilibrium. Okay? So what's happening is our starting acetate at 1.0 and our starting acetic acid at 1.0 are now going to be affected by this HCl. That HCl is going to react, causing a decrease in the concentration of acetate. But where does the acetate go when it reacts? It goes to the products, which means the acetate must go up. Sorry, acetic acid must go up. What does this mean? We have new initial conditions within our ice table. If we wanted to go an ice table route, we have 0.9 and we have 1.1. We could now flow through the ice chart and do all the ice chart calculations with a new chemical reaction, okay, looking at the balance of those particular ions and the production of H+. Or what we could go through and do, our pKa equals, I already forgot the freaking formula. Like I said, I seriously don't hold this in my head. Was it CH3COO minus on top? Yeah. Plus our pH. Okay, we could solve for the pH by transferring this giant chunk of a beast over to the other side. And then we just sub in all those numbers. Make sense? Okay. Why do we need some kind of special expression to go through and solve this? Why not just use an ice table every single time? Is this faster than an ice table? Yeah, that's why. Okay. This process is significantly faster than dealing with an ice table and looking at how each of those concentrations move up and down. So what we try to do is create a system that allows us to run calculations faster. But why do we need to run calculations faster?
Time limit.
Okay, we could say time limit. Time limit on what? You could say, well, your quizzes. So this was invented just because of quizzes? It's more efficient. Why is it more efficient? Some chemicals don't wait all day to combine. What else could we look at? 38 should be good. Comes in with that key word up at the top. Keyword that we had not yet addressed. Buffer. Okay. Buffers are very, very important chemical systems that allow for the maintenance of pH. So if we go through and run the calculation here, what we will see is the pH does decrease, but it's not going to decrease by that much. If we had just added 0.1 molar HCl to just plain water, we would have seen a massive drop in the pH. Okay? So our buffer system maintains the pH within a relatively narrow range. That becomes nice because that allows us to ensure that we don't get huge effects if we accidentally get dunked in acid. Okay? Our system would allow us to neutralize some of that and maintain our current levels. Why is that important? Remember when we talked about denaturing proteins? Biological systems have to be maintained at a certain pH. Those biological systems have lots of acid-base characteristics associated with them, and if you start changing the pH, you change their structure. And if their structure changes, the intermolecular forces change. And if the intermolecular forces change, the whole system falls apart. Okay, so all biological systems run at a particular pH. And we use different buffer systems to maintain that for whatever we're trying to study or monitor. Okay, so if I remember this right, 65. This is your Henderson-Hasselbalch equation. Note it has been rearranged. Okay. In the rearrangement, there's some things that I want you to be aware of that can get confusing. This notation is actually one of the better notations, though there is a weird secondary minus there. I don't know why. You'll sometimes see this written as base over acid, and that gets really tricky because in that previous question, what did we add? We had the acetic acid and we had acetate, and then what did we add? HCl, and HCl is an acid. Is that number appearing in our pKa expression or our Henderson-Hasselbalch? No. Okay, what's appearing in the Henderson-Hasselbalch equation is the acid and the conjugate base, okay, of whatever your buffer system is. So you have to be real careful with making sure you're inputting the correct concentrations for each of those states. Okay? If we go through and look at the question here, this is what I asked you to just go through and solve. Okay? We can do this with an ice table, or you can do it with Henderson-Hasselbalch. Both of them go through and run the exact same process. Kind of, sort of? Let's see, how did I want to do this? I want to go to 60. I think that means I want to go back to 53. Yeah, I want to go back to 53. I wanted to make sure we got the Henderson-Hasselbalch down and out of the way because that is an important expression. We're going to come back to it again in a little bit, but at least we've got some context. Here we've got carbonate, a weak base. Write the reaction that occurs between carbonate and acetic acid. Write the equilibrium constant for the expression for this reaction. This should be fast. I think this question was intending to ask something else, but we'll see where it goes. So if we go through and look at our carbonate reacting with H3O+, okay, what do you think carbonate will act as?
Base.
Why a base?
It says it's weak base.
Okay, cool. It says it's a weak base. Why else do you think it would act as a base? There's no hydrogen, which means it can't act as an acid. Okay? So leverage the content you know. If it's going to act as a base, what needs to happen to its structure? What was the definition of a base? Gain a hydrogen, which means when we draw out the product, we should see a hydrogen added to it. Why did the charge change? Why did the charge change? H plus was added. You're taking a -2 species and you're combining it with a positive species. Those charges should cancel and set you up with that negative charge. Write the equilibrium constant for this expression. We're looking at our products over our reactants. And I think this looks a bit goofy because, again, I think there was something else intended for this. Kind of makes sense? Okay. How does a decrease in the pH affect the solubility of calcium carbonate? It's a blue box. Technically, you could talk through it, or you could talk out loud. You guys want to talk at your tables? Is that easier? Sure? Okay, let's try that. So cool, what happens? We've got a lot of equations here. Let's pick the equation that's most relevant to the question. It's interesting you say the top one. I would argue the bottom one, but let's go with the top one. Why do you think the top one's the most relevant?
Well, if we're talking pH, that's the concentration of H3O plus.
Cool. So when we see the statement decrease in pH, what does that mean? That would be something that could be asked in a quiz to say, please explain what this means. Not you, because you started it. What's that? More acidic. Fair. What else does it mean?
Concentration of H plus.
We're looking at the concentration of H3O plus going up. Okay? Saying more acidic isn't wrong, but does saying more acidic mean anything to our chemical expressions? If you knew what acidity was, in which case, don't go through the more acidic, go directly to the thing that was relevant. Okay, so we're talking about an increase of H3O plus. Okay, what is that increase in H3O plus supposed to affect? The solubility of our calcium carbonate. So if we're now looking at these two questions or these two equations, which of those do you think is more relevant? I would lean towards the bottom. The question is actually asking about the solubility of calcium carbonate. Right? Where do we have calcium carbonate? That's in the bottom expression. Does that mean the top expression isn't valuable? Entirely not. Okay? It is still valuable, but we have to address or frame where our conversation is about. What we're talking about is the effect on the solubility of the calcium carbonate. So calcium carbonate is going to dissolve to form some concentration of our calcium ions and our carbonates. Do you like numbers or variables? Numbers. Okay, let's form 0.1 of each of those. Okay, at equilibrium. Do we care what the calcium carbonate concentration is going to be? No, why not? It's a solid. Its concentration isn't changing, so I don't care. So if we just go through and say those are 0.1, that's where we're at. Okay? Officially, they're not. We would have to go through and solve for it to figure out what it was using our KSP. And if you want to do that practice, we can do that practice also. What's going to happen if I now add H3O plus into this? Which is a strange statement, right? Add H plus, even though I'm decreasing. This is why it's important to tie in what those things meant. If I add H3O plus, what would that plus interact with in our solution? It's going to interact with a negative. So we look at our solution and say, what is negative? Is it the calcium ion or the carbonate ion? The carbonate ion. So if it's going to interact with that, what we're now talking about is a secondary reaction with the CO3 minus 2. Wow. If I add H plus, what happens? HCO3 minus. Okay? Technically with how I've written just H3O. I should actually stick to the notation you guys have been working with, H3O plus. Does Alex show H3O plus or does it show H plus? H3O? Okay, let's stick with that. So we would write out that expression. Does that expression look familiar? Yeah, where's that expression showing up? That's the very top expression. Right? So what we're saying is when we add H3O plus, this chemical reaction happens. How do we know it happens? How do we know it progresses towards products at all? There it is. If we look at the K expression for that chemical reaction, HCO3 minus over our CO3 minus 2 plus our H3O plus. I don't know why I wrote a plus there. Okay. That K value gives us some information. It's larger than 1, which means what happens to the concentration of HCO3 minus? It's favored. This reaction favors the products. So when I add H+, what happens to the concentration of carbonate ion? It decreases. And if I decrease the carbonate ion, how's that going to affect that primary equilibrium, the one I was actually asked about? Le Chatelier, I start to remove product. What does the reaction do? It shifts to the right to replace that product, which means what has to happen to my calcium carbonate? It has to decrease. I'm increasing the solubility of the compound because the solid value is decreasing. So pH has a huge effect on our calcium carbonate ion. Okay? Again, this is our common ion effect. What we're saying is, how does changing the pH react with our individual species? I can do this with OH minus as well. Okay? If I add OH minus, what's the OH minus going to react with? What is that negative going to react with? A positive. So I go back to my primary equation, the one that's driving my question, and I say, which thing is positive? My calcium ion. What would happen? I'd form my calcium hydroxide. Could even go through and balance that if we really wanted to. To decide if increasing the pH, i.e. making it more basic, increasing our hydroxide ion concentration, was going to have an effect, what do I need to know about this equation, this reaction that I just wrote out?
Okay.
I need to know its K value. Okay? That's why the K value was initially given for that first equation. Just because it's listed first doesn't mean it's the most important to the question. Kind of makes sense. What if you didn't know the K value? Leaning into Alex. What if you didn't know this K value? What's that? Doing an ice table is still going to get you an equilibrium concentration that's going to take you to a K, and you don't know the actual concentrations of those things, so you wouldn't be able to solve for K. Look it up. That's what you're supposed to do with Alex, is look up those K expressions. Okay? You're not expected to have them memorized in most circumstances. Where's that slim circumstance that you are expected to have it? Actually, you're not even supposed to have it memorized there. I lied. I forgot. The slim circumstance that if I was your official teacher that you would have to have it memorized would be, you do have it memorized for water too, but more than likely incidentally. Strong acids and bases. Right? You should know the strong acids and bases, because if this was a strong base, shows how well I have it memorized. If this was a strong base, what does that do? It completely dissociates. If it completely dissociated, is the hydroxide reacting with the calcium? No. So the hydroxide would have no effect on this chemical reaction. It only has an effect if you're looking at weak acid-base systems. Kind of, sort of? Okay. Is today Monday? Is that what's going on? At least somebody let out a slight gasp. Ocean acidification messes with our solubility of calcium carbonate, which is why we end up seeing our shells effectively dissolve. So our ionic compounds is affected by pH if they contain our weak acids and bases, okay, which is literally what we just said. The strong acids and bases don't have an effect, okay, if we're making them, but if they're containing weak acids or bases, we're good. Good. Good in a bad sense, because it means we have to think about that chemical reaction. Acids can remove hard water deposits, mostly because our hard water deposits tend to be things like calcium carbonate. So we can add an acid to that to help it dissolve. This is where we use CLR or vinegar, because all two of those things have acetic acid or some level of acid in them. That acid helps to work in there, increase the solubility of our calcium carbonate, and clean up our appliances. Okay? So if you got a hot date coming over, you should clean up your stuff. Just pour acid over everything. Sounds kind of dangerous. Okay? Acid-base reactions are equilibrium systems. So if we change our concentration of the reaction or product, the reaction will respond to reestablish our equilibrium. Said another way, this is Le Chatelier. This is what we learned in the past unit. We're now looking at the specific examples of how it applies to particular chemical reactions. So if we're looking at this reaction initially at equilibrium, what happens if we start to make changes? If we add more acetic acid, if we increase the concentration of acetic acid, what's going to happen? The reaction is going to shift to the right. Okay, dang, you actually said that right. I totally thought you had it wrong. See, that's why I got to write it down. Okay, it shifts to the right, which means the concentration of H3O plus goes up. And if the concentration of H3O plus goes up, the pH goes down. Okay, so you should be focusing on what's happening with the actual species within the chemical reaction. Once you have those, you can take that next leap to what's happening with your pHs, your interpretations of those chemical equations. What if acetate was added to the reaction? By increase the concentration of acetate, what's our equilibrium want to do? Shift to the left, which means what happens to our pH? The pH is going to go up because that H3O plus concentration has to go down to allow for the reaction to shift towards the reactants. Make sense? Okay. So our buffer is a system that contains approximately equal amounts of the weak acid and its conjugate base. So the intent of the buffer system is if we have both of those present, what happens when I add H+? Well, actually, let's get rid of the buffer system. No buffer system. And I add H+. What's going to happen to the pH? It's going to go down. And it should go down really fast because H+ is directly tied to that H+ concentration. Okay? But if I have a buffer system, what happens when I add the H+? What does the positive react with? The negative conjugate base, which then means what happens to the concentration of H+? I added it, but it reacts away, which means what should happen to the pH? If I add H+, it should go straight down. But if I add H+, and there's a weak base there, the H+ reacts with the base, do I have any more H+? No, which means what happens to the pH? It stays the same. Okay? So if I have a little bit of a weak base present, that weak base can effectively sponge out all that extra H+ so that I never see the pH change. What if I add a bunch of hydroxide? What's the hydroxide going to react with? It's going to react with the weak acid, which means the hydroxide concentration gets sponged away by our weak acid. What's the net result? No change in the pH. Last week when you guys did the titration, you titrated HCl, right, and you did acetic acid. The acetic acid maintained a roughly constant pH until you overwhelmed it with the hydroxide that you were titrating in. Right? The other one, you're like, well, but it maintained as well too. But where did it maintain? It maintained at a very low pH scale. because all that was present was really just acid. So it went from acid to base. There wasn't a middle ground. So depending on your buffer system, you get a little bit of a middle ground that expands the kind of stability of your pH within that range. So buffers maintain constant pH, which is important for really all biological systems. Right? Henderson-Hasselbalch coming back again. Right? Just wanted to make sure we covered it first. The Henderson-Hasselbalch is a way to describe what's going on within our buffers. Buffers become such a valuable system for study within all biological systems, so every biochemistry course ever run uses buffer systems. Right? Because they're running those buffer systems so much, they want to have a good understanding of the relationship between the pH and the pKa and what that's going to mean for the conjugate base in the acid. Right? To give you a little bit of a parlay into the future, if you needed to take a biochemistry class, okay, what are proteins made out of? Amino acids. So amino is referring to the nitrogen. The acid is referring to a carboxylic acid functional group. Both of these functional groups have some chemistry associated with them. The acid has what functional chemistry associated with it? The acid has what chemistry associated with it? It's very redundant. It acts as an acid, yes. Okay? What does the amine have going with it? Well, if you break down the amine name, it's obvious. Amine sounds just like base. Thank you. It was a joke. Okay? And if we're going through and dealing with our Henderson-Hasselbalch system, when we're talking about our amino acids, really what we're talking about up here is the deprotonated state and the protonated state. Okay? Where we have the hydrogen on the structure versus off the structure. What's going to happen with the acid? Well, when we have that hydrogen on there, that's our protonated state. And if we run a chemical reaction, we can take it to the deprotonated state. That chemical reaction is going to depend on the concentration of hydrogen ions or hydroxide ions in solution. And we could track that by looking at the pH. So if I change the pH, I can change that protonated versus deprotonated state. Why does that become valuable to me as a biochemist? Biochemists study biological systems like proteins, and proteins are made up of amino acids. And if I change the pH, what happens to the protonation state? It changes it, which means the charge changes, and if the charge changes, so does its solubility. So does its intermolecular forces with the outside world. So I could now go through and create systems to separate or isolate individual proteins based off of changing the pH. That's a pretty powerful thing, and so I want to be aware of those abilities to run those calculations. That's where Henderson-Hasselbalch is going to come in and scream at you later on in life. Okay? If you don't need more chemistry, then you don't have to stress about it. But everybody that does, it's going to show up in organic chemistry and it's going to show up in biochemistry. Biochemistry is like the God level area for it. Right now, we're just trying to set you up so you can run those calculations and be like, yay, numbers. Okay? Organic chemistry, we look at it as a relatively simple system, and then biochemistry takes it all to a whole new level. Okay? What's happening on the base side? This is your deprotonated state, and it goes to the protonated state. What dictates whether it's protonated or deprotonated? Both the pH and the pKa. It's the identity of the individual species, that functional group. So you would look at the relationship between your pH and pKa, and that would define whether you have more protonated or deprotonated state. ultimately people will just go through and cheat their way through that by ballparking estimates. Cheat is a harsh word. It's not cheat. Okay? You're just manipulating the equation to get to a place where you can just memorize your way out of it. Do you want to go through and look at this and solve? Otherwise, we can keep running through slides, which at this point I think is just content. So it's going to come down to what you want. Do you want practice, or do you want more content? So what do you guys want? Practice? There it is. Ah. So, and again, I don't have freaking memorized. I hate this stupid expression. Was that plus log base over acid? So our pH equals our pKa plus the log A minus over HA. So this question is asking for the ratio. So what it's asking for is that magic number in there. Okay, so what we'll do is push through to get that ratio, that numerical value, and then we'll talk about what that means. Okay, so if the pH is 3.75, 3.75 equals my pKa. My pKa is 4.75 plus the log of my magic ratio, which I'll just call R. So to simplify, I'm going to get -1 equals log of R. Does everybody agree? 3.75 minus the 4.75 from both sides. Pretty sure I did that math right. I can then take the antilog of both sides. What's the antilog? Power of 10. That power of 10 cancels out, and I get the magic ratio of R equals 10 to 0.
0.
Oh, sorry. Selective hearing, and it was bad hearing. 10 to the -1, or if we wanted to look at this differently, 0.1. What does that mean? We'll stop. What's the question?
10 to the 1.
3.75, I back up from our equation. We take 4.75, we subtract it from both sides, which means 4.75. 3.75 minus 4.75 is -1.
But isn't it 10 to the negative?
Well, this is just anti-log.
So what you're thinking about is how we convert P or H plus into pH. We're not doing any of those conversions here. All we're trying to do is get rid of the log on the other side. Okay? So it's not holding it to the 10 to the negative power or doing negative logs or any of that. All we're doing is direct solve out of the expression. To get rid of the log, I just have to do 10 to the log. That gets rid of the log. So I'll take the 10 power of 10 to both sides of the equation, and I'm going to get 10 to the -1. 10 to the log of my R, the log and 10 will cancel, and I'll just get R. So R should equal 10 to the -1, 0.1. Does that help? Are you just saying yes, so I go on?
I thought 10 to the -1 is 1.
Enter it in the calculator.
That's weird.
10 to the -1 means you're shifting your decimal. It's officially 1 times 10 to the -1. You're shifting the decimal place 1 place to the left. It's going to be 0.1. Say again?
10 to the 0 is 1.
Yeah, 10 to the 0 is 1. Okay. Which, it's going to sound like it's directed at you, but I guarantee there's other people that make that same kind of mistake. Are you allowed a calculator on the test? Yes. If you're allowed that calculator, even if you think it's a simple calculation, you can double check your work by running it through the calculator. Does that make sense? That can minimize some of those simple mistakes. Right? I would do it all the time with our conversions, dealing with kilos and millis, shifting the decimal place the wrong direction. Right? So I would always recommend using the calculator to ensure that you don't screw that up. Right? So what does it mean to have this ratio of b 0.1?
Just the ratio of concentration of the acid and
Okay, so our CH3COO minus over CH3COOH is equal to 0.1. What does that mean? Yeah, it's the ratio, but what does it mean? When the pH is 3.75, I get that number. What does that number mean?
You have more acid on conjugate base.
I have more of my acid than I have of my conjugate base. That's why I'm getting a value less than 1. Did everybody catch that? Because that's the important line. That's the thing that you use when we draw out amino acids. That's what you're evaluating. You're looking at that ratio and seeing where its magnitude is. If it's a value under 1, we have more of the protonated state than we have of the deprotonated state. If it's a value greater than 1, what does that mean? Deprotonated must be in a larger concentration than the protonated. We're looking at our deprotonated on stop, whatever that is, top, and our protonated on the bottom. Kind of, sort of? You guys good? Think you can do it?
Quick question.
Yes.
The Henderson-Hasselbalch equation, did you say the base was on top and the acids on the bottom?
Yeah, and that's, be
Well,
careful,
yeah.
calling it base and acid, but yes. What I would prefer instead, which no one's going to want to write down, would be the conjugate base is on top and the acid is on the bottom. But that's a whole hell of a lot more words to kind of manipulate.
Gotcha. Thank you.
Okay? So you guys ready to do it? 5.75? Okay, do it. What do we get for R? So when the pH is 5.75, what do we get? I saw like half a dozen people write it down. What did you get for R? It was not 0. 10, thank you. Okay, we get a 10. What does that mean? There's more of our conjugate base present under these new circumstances than there was of our acid. Stupid pen. So if we pay attention real carefully, let's backtrack out of some of this. Let's actually clear away almost all of that work. Are you making fun of me saying make sure to use a calculator?
He just got his math wrong.
Oh, so yes, you should make sure to use calculator then.
How much is usage?
No. Nice try though. All right. So when the pH was 3.75, we had more of the protonated state, right? That was, I think I said that out loud, right? I did? Okay. Okay, so yes, I did. When the pH is 3.75, we have more of the protonated state, right?
Yes.
Yes, cool. When the pH was 5.75, we have more of the deprotonated state. What happens if I make the pH 10? More deprotonated. What if I make the pH 1? More protonated. So at least 2 people have caught on to recognizing the value of those numbers. What are you comparing in each of these cases? The pH and the pKa. It's the relative space between those two that dictates it. If your pH is lower than the pKa, what does that mean happens? More of the protonated, more of the acid is formed. If your pH is larger than the pKa, what does that mean? More of the deprotonated state. That comparison is what you ultimately end up using in biochem. Very, very swiftly, you get a quick interpretation of which state is more prevalent, the protonated or the deprotonated state. Okay? The extra layer that goes with this is then what does that structurally mean as far as charges go, and that's outside the scope of this class, so don't stress on that. But realize that is coming down the pike for you if you're dealing with biochem or OChem. Okay? But if you understand that relationship and have that nailed down, you've got a good leap ahead of the competition when it comes to those relationships. Kind of, sort of? So, buffers are most effective when the pH is plus or minus 1 from the pKa. And so what this slide is going through and doing is looking at the relationship between your pH and pKa and how much stuff is present. Okay? If we slide to a pH that is very, very low, okay, what happens to the concentration of A minus? It's going to drastically drop, which means as we add more H plus, do we have any A minus to sponge away the H plus? No, the concentration is really low. Right? If we look at it conversely, and we now go through and we go to a very large pH. A large pH means we're looking at a more basic environment. Okay, fudge knuckles. What is the base going to react with? Our acid. Now as I continue to add more base, there's less and less acid present to sponge away that base. Which means now I'm going to see that change in pH happen a little bit more sharply. Kind of makes sense? This becomes valuable to us because when we look at systems, we're going to try to study them at particular pHs. Okay? And if we want to study them at a pH, we need to know the buffer system that allows us to study it in that proper pH range. Okay? Sometimes we'll be like, well, why can't you just use the organism itself? The organism itself has lots of other buffer systems at play, and that could convolute what you're studying. Okay, so if you're trying to study how a protein functions, you need to pull that protein out and study it independent of everything else. Okay, that means you have to find a buffer system that targets that pH range appropriately. So if you understand your pH needing to be ballpark equal to your pKa, that can help you target your buffers to zero in on the appropriate pH scale. Oops, nope. Why'd you not move? I just locked up. So what happens to the pH of a buffer when a strong acid such as HCl is added? Should just be a talk through at this point. What happens when HCl is added to water? It dissociates completely, which means what happens to the pH? It drops through the floor almost instantly. Okay? If I do that same addition to an acetic acid acetate buffer system, what happens? What's the H plus do? It reacts with the buffer, changing the concentration of our H plus, which then means the pH stays relatively the same. Okay? Water doesn't do a good job of buffering, okay, because of its pKa value. Okay? It's way up outside of our pH scale. Our acetic acid acetate now has a pH or a pKa that's within that range that allows us to buffer that system out. So we could quantify it. In this case, what is your pH going to be? This is why we're doing all these stupid pH. What's your H plus concentration going to be? Like, I can't calculate that. Yeah, you can. What's the H plus concentration? Say it again.
0.1.
It is 0.1. It is 0.1 because HCl is a strong acid. Again, if we have that information at the back of our fingertips, we can quickly jump to conclusions on this. HCl is a strong acid. Since it's a strong acid, it completely dissociates, which means H3O plus is going to be equal to the starting concentration of our acid, and I get 0.1. Could I calculate the pH? Yeah, pH is not 10 to the negative. The negative log of our H plus concentration, the other 10. Use a calculator. All right? We went through and did this one as a quick example back when we talked about the Henderson-Hassel, that one. Do you guys want to try and do this one now again on your own, now that we've gone and talked about other things and gotten lost and confused and dazed? Or do you think you got it? Got it. Cool. Okay. The pH of your buffer only changes a little bit. Okay. Same deal. We've now talked through this multiple times. Your added strong acid reacts with the base component of whatever your buffer is. That base component could be negatively charged. It could also be neutral. It just depends on the individual system. Since we're talking about acids as our buffers, typically what you're going to see is HA and A minus when we talk through these. Okay. The same thing happens with our hydroxide. Your body contains lots of different buffers that maintain a constant pH in your different environments. So blood, stomach, and all that fun stuff. Okay? So this is a fun one. You can buy, alkaline water. I was going to say basified water, but alkaline water sounds cooler. And everyone goes, oh, it's the greatest thing ever. What is that alkaline water going to do? For once, we're correct. Nothing. No response. Yeah, it does absolutely nothing to our system. Okay? We're not going to see a sizable effect in this because what we're doing is dropping that basified water into our stomach, which has acid in it, which is really at best just going to neutralize that. If you had an acid reflux issue, maybe it would do something then. But even then, the amount that it's alkaline is next to nothing. It's going to get wiped out almost instantly.
So you paid $3 extra for no reason?
Yep. Welcome to marketing. Okay, so how to go through and make a buffer. Okay, your buffers are made in labs, and ultimately what you're going through and doing is looking at targeting your pKa to the pH range you want. Okay, so depending on what you're trying to do, you're just picking a system that matches as closely as possible. Okay, remember we said we wanted that pH to equal our pKa. What would be our best buffer in this case? Our NH4 plus. Okay, that targets our pH of 9 as best as possible, or as close as possible. Kind of, sort of? Why am I excited? Do you guys actually want to go through and do that? Oh, actually, never mind. I thought we had a couple more minutes. We did not. Okay.
Nowhere to go.
So we are officially done. The quiz is on the next day, Wednesday. I do want to make one